chapters. Today's chapter is page equilibrium. So previous class we have discussed the chapters, that is chemical equilibrium. Chemical equilibrium we have already completed, and the chapters ionic equilibrium also we completed. So third chapters today we are going to start, that phase equilibrium. So in these chapters we discuss details about of the equilibriums and equilibrium constants and all the characteristics of equilibrium. So we understand that what do we mean by equilibrium. So if we simply say that equilibrium is a stable state of the reactions. So any states which is highly stable of that reactions, then that is called the equilibrium state of the reactions, or the stable state of the reactions. So these chapters said that phase equilibrium. So in this chapter, phase equilibrium, so two parts. One is phase. So if we say that phase, it is a heterogeneous and physically distinct and mechanically separable of a systems is called that phase. So if we say that phase, it will like to say that phase means like if we says anything in the solutions. So what we see in the naked eye to this beaker, here we see that solution is present. So only that solution is present, and it will look in our naked eyes that only one thing you are actually seeing in this naked eye. So if you say a glass of water, on that about what glass, so what you says over there, only water you are seeing. So only water means that is phase 1. Okay. So here phase equal to 1, and at the same time when I said here water is there, with that I added some stones. I added some stones. Okay. I added some stones. The stones is present. So what we see in our naked eye, what you see is that with water about this beaker, what you see is here with water some stones also present. So here that phase equal to 2. Okay, so phase means what we see in our naked eye, how many different states is present in our present, so that is called the phase. So in this in this case, what suppose this is glass, then in the glass only water is there, so only water is phase is 1, it's 1 only present, so 1. And in this water, in this glass or beaker, what we say that with water stone also there. So two types of things is present that we see in the naked eyes, so that phase equal to 2. So you understand that what I mean by phase means how many distinct objects are present. So phase means if we say that phase means that heterogeneous and physically distinct and mechanically separable. I mean that here we can separate the stone from this water, so mechanically separable of a system is called the phase. Means how many different things is present, that is called the, means that how many different things that is by our naked eyes. Okay, so if we says that, let's say what is there, on that time what I do, I add that sugar. What I add sugar, then the sugar is easily dissolved in water. So after adding sugar also it will look the same. So here the page is 1, but we added the sugar, but in our naked eyes that we can't see it is a homogeneous, so that page is 1. So which is distinct by our naked eyes. So if we distinct two things, then page will be 2. If it distinct only one, then page is 1. Okay, so page equilibrium means that page of a different substance, different object or substance, if they exist in equilibriums, then that we call the page equilibrium. So while we proceed this chapters, we understand that different state of substances, they will exist in a equilibrium. So some rules we will discuss that about the page, like how to distinguish the page. So some rules are there, some rules. Let's say that the same things, like if you have a object that is solids, and we have that another B, and this is also solids, and C, that is also solids, and if you mix, then one mixture will come, right? If you mix that A solid, B solid, C solid, like if you mix A is rock, and this is bricks, and this is any like any metal, so if you mix, then one mixture will come. So what are the pages are there in this mixture? What are the pages is there? So in our naked eyes, so rocks will looks like this. Let's say suppose like this. I am taking like this. Suppose everything is spherical rocks. Let's say, and bricks which looks like this, and metals. Let's say that looks like this. Okay. So in this, in our naked eyes, what we say is that it will look three things. This is all. Naked eyes, this looks different. This looks different. This looks different. So the page is equal to 3. Okay, so if all are solids, then the number of page is equal to number of solids present in mixture. Okay, and we will discuss that second rule. Like we take the solids, let me take that gases. Let's say A gas plus B of gas plus C of gas, that will give one mixture. Okay, so now if I say that how many pages are there, so in our naked eyes we not see the gas first thing. So if we not look in our naked eyes, then what you say that by looking this, it looks like everything is same, means it looks that only one thing you are looking, although you are not able to see the gas. So if you simply ask that what you are seeing, then I am seeing only one thing, that is gas is there, A gas, B gas, C gas. Suppose in this like one bag or one we take, here that gases is there, A gas plus B gas plus C gas is there. So if you see in your naked eye, then it look only same. Okay, so what is say that page is 1, because we can't distinguish this in the naked eye. So number of page page equal to 1 if gases are present. If only gases are present. If only gases are present. How many? Like it may be D of gas, infinite number of gases is present. Then also like it look the same. So because we not able to see the gas first thing in the naked eye. So if only gases are present, then page is 1. Okay. Then we will discuss the third point. So we'll see that solids is present, then what and gases is present, then what are the pages. So third we will take that if liquids is present. Let's say A, this is liquid, and B is liquids, and we mix it. The mixture H4. So let's say I am taking 1 liquids and let's say that other liquids, that's other liquids. Let's say its color is, because I take the different color because I take this is other liquids. Let's say this is B liquids and this is A liquids. So if you add it, then what will happen, that this depend on that whether this after mixing whether it is completely dissolved or not, completely soluble or not. If A and B is completely soluble, then that will give the homogeneous mixture. If it is completely dissolved, like A is completely dissolved on B, then it is homogeneous. Means if it is completely dissolved, like if you say this is water, A is water, and this is, let's say ethanol, then this is completely dissolved. Then after that mixture also we will get like this homogeneous. On that case, if it is completely dissolved and give the homogeneous, then A is equal to 1. Okay, but water, and also if you take like this is what, the polar solvents, this is also polar solvents, this is also the polar solvents. So if you take the polar solvents, then they are completely dissolved and that give homogeneous solutions and page is 1. But also if you say non-polar solvents, polar plus polar. Okay, similarly benzene, that is non-polar, and another non-polar if you take CCl4, non-polar solvents, then also you will get the homogeneous mixture, and again the page equal to 1. But if you take any one polar solvents and another is non-polar solvents, let's say you take that polar solvents, let's say water, a non-polar solvent, let's say you take the benzene. Then the mixtures will be heterogeneous because that will be not completely dissolved, so that will get heterogeneous mixture, and page is 2. Okay, so you have to remember that this is polar and this is non-polar. So you have to remember that for solid cases, if you are taking 2 polar solvents, then that will going to give homogeneous mixtures and page is 1. And similarly, if you take 2 non-polar solvents, then that will also give homogeneous and page equal to 1. But if you take one polar and other is non-polar, then the mixture is heterogeneous and page is equal to 2. Okay, so 3 cases we discussed. What will happen if 2 liquids you add, what happened if 2 gases if you add, what happened if we add 2 solids. Now is case for what he says. Hmm. So we take the individually, like if you taking two liquids, if you taking two solids, if you taking two gases only. What happens if I take one as liquid and other as, let's say, solid? Then what will be the mixture and what is the pH? So if you add one solids and one liquids, then what happened that the mixture, if solids and liquid, if that mixture is homogeneous or not. Okay, same case, if it is homogeneous, then pH equal to 1. What the example? Let's say I am taking that water, that is liquid, yes, and let's say I am taking the sugar, that is solids. So if you add it, then here for this case, this is the mixture is, so sugar is completely dissolved in water, so mixture is homogeneous. So pH equal to 1. And here also some cases we say that if I taken this is water and let's say I am adding sugar. So here 2 points is there, like before saturation point. Saturation point means we know that saturation point is that state where neither solids or liquids, like after saturation point is that most stable point, like equilibrium point. Saturation point is the most stable point. After saturation point, that sugar will not dissolve, and before saturation point more sugar can dissolve. Okay, so before saturation points means sugar can dissolve, so on that case pH equal to 1. But after saturation point, sugar is not able to dissolve, so sugar will be stay like this in water, and sugar we can see the two things, so on that case pH is 2. Okay, these things. And if we say that I am adding water, similarly if I add water liquid plus any solids, like I add rocks, on that case it is not, the mixture is not completely dissolved, so this will give heterogeneous. On that case pH equal to 2. Okay, and if I am adding which it dissolves, then the mixture is homogeneous, then pH is 1. On that time the 2 points is there. Before saturation point pH is 1, and after saturation point where no more sugar is dissolved, on that case pH is equal to 2. And if we are adding which is not completely dissolved, then that is going to give heterogeneous, and that is pH equal to 2. So I add solids and liquids. Similarly, if I add A is gas plus B is liquid. So in third cases I add A solids and B is liquid. Now I am adding A gas and B is liquid. Then that will give mixture. Yes. Now so here that page is what you see in naked eyes. So if like here in this things, what that liquid is there and gas is also there. So what is that, if anybody says that in this sir, although in naked eyes if we see only we see the liquids, but the person will say that here gas is there and liquid is there, then what we say that okay, up to this gas liquid is there, then the above has to be gas, so pH equal to 2, because this gas will give 1 pH and liquid will give 1 pH, so total equal to pH is 2. But in naked eye you will see only liquids, but he says that here liquids and gases is there. So okay, so we say that he already says that gas is there. So in your naked eye you only seeing that liquids, but he mentioned that gas is also there, so you take gas is one page and liquid is another page, so total page is 2. But if he says that A gas and B liquids, and that is going to give mixture, and A gas has high van der Waals force, high van der Waals forces is there, then what is says high van der Waals forces means this is A gas can easily liquefy. Easily liquefy means that this A gas will convert into liquids and B also liquids. So that mixture, what is say that if two liquids is homogeneous, then the mixture will give pH equal to 1. Okay. So here that if not mentions anything, then we says that pH is 2. But if he says that A gas is having high van der Waals forces, then assume that A will liquefy gas and A gas is easily liquefied to liquid, so A liquids, B liquids, and totally give a mixture, and that mixture is homogeneous. Assume that is homogeneous, then pH is equal to 1. Okay, so we see that if we add solid plus liquids, then what happened? We also see that loss gases plus liquids, then what will happen? And third case, if we add that gas plus solids, then what will happen? So I'll say A gas plus B solids. Then these solids, they can't be mixed, means that the mixture, they cannot be mixable. So what it says that for gas 1 page, for liquids, so for solid 1 page, so total page equal to 2. Okay, so here A gas will not solidified into solid, so it can be liquefied, but solidified is very less. So always assume that pH equal to 2. If one solid and one gas is there, then pH is 2. So gas will give one pH and liquids will give other pH. Or if you say that A gas plus B gas plus C solids plus D solid plus E solids, then in the mixture, what is the pH? Means this, assume that all gases give pH 1, pH equal to 1, and the solids will give different pHs, so pH is 3, so total pH is 1. Okay, so we discussed that in different cases, if solids is given, if only solids is given, what is the pHs? If only liquids are given, then what is the pH? And if only gases is given, what is the pHs? What is the pH? And if solid plus liquids is added, then what will be the pH? And if liquid plus solid is given, what is the pH? And if gas plus solid is given, what is the pH? So we discussed the different possibilities of the mixture. So now we will discuss that. We have discussed up to case 4. Okay. So next case is if in a mixture what is that? Mixtures allotropes is there. Okay, in a mixtures allotropes is present. Let's say in a mixture carbon, so carbon says allotropes of, but that is graphite and diamond and C60. So if the carbon is present and if the allotropes of, like if it says in this mixture carbon of C60 is present plus carbon of graphite is present plus carbon of diamond is present plus any B solid is present. Then in the mixture, what is the pH? Then allotropes number of pH equal to allotropes of substances. So here that how many 3 allotropes is there, so pH is 3 for carbon. Okay, so here that 3 plus this is another one plus 1, so total is 4, so pH equal to 4. Okay, so if different allotropes of a substance is given, then consider all the allotropes in a different pages. Okay, so allotropes will give different pages. And fifth case, this is sixth case. Okay, so sixth case, any alloys give pH equal to 1. What is it? Like if we say Zn solid plus copper solid. So we discussed the case 1 or case 2 something. Case 1 we discussed that if solids is present, then we take that all solids give different pH. So according to the rule 1, this has to be given pH, this has to be given pH. So pH equal to 2, but no. Why? Because these mixtures will form one alloy, that is brass, and this brass will give pH equal to 1. So here pH is not equal to 2, pH equal to 1, not pH equal to 2. So if brass is forming, then that will give only one pH, because if you see in our naked eye, this brass looks the same. So this is a homogeneous mixture. Okay, so you have to remember this. And any other rules? Any other rules are left? Allotropes, okay, alloys, okay. Another rules. Rules is like hydrates. Each hydrates gives individual pH. What it says? Let's say Cu SO4 plus 5H2O. This is one solids, and if we heat it, then this will become what? CuSO4 3H2O. This is also solid, and again if we heat it, then CuSO4 H2O. This is going to give heat, then we are going to give again CuSO4. So each hydrates give one pH. So this is pH equal to 1. This is one pH. This is one pH. This is one pH. So in these solutions, the pH equal to 4. So each hydrates give individual pH. Okay, so 4 hydrates we can pour, means 4 pHs we get. So this is all about of the pH. Another important terms we will use while studying this pH equilibrium, that is components. Okay, what is components? It is that which we defines to explain that state of that systems. So if we say that we will discuss while we are proceeding this chapter. So mathematically, what you say, this component represented by C. So this C equal to S minus R. Okay, so what do you mean by this S? S is any species which exists individually in pre-states. Like it may be any ions or it may be any molecules, but S can't be intermediates because it not exist in pre-state, intermediate or transition state. So S can't be intermediate or can't be transition state. So if it says that example, we are taking that Haber process. So what is that? N2 gas plus H2 gas, that is going to give ammonia gas. So here this is also exist freely, this also exist freely, this also exist freely. So this everybody gives, everybody has independent existence. So total S is how many species? 1, 2, 3, and R means any conditions. R is any conditions or this equilibrium states. Okay, so here that how many species are there? Component means S minus R. So how many individual exist species are there? This 1, 2, 3, that is 3. And what are the condition? Condition is equilibrium state is given this sign, so this is 1. So components is 2. Okay. So this will clear more when we proceed these chapters. And next topics is okay. Before going to that, another things you have to discuss that let's say N2 gas plus H2 gas and going to give NH3 gas. Okay. If conditions given that initially that we are taking like chemically we already discussed that at T equal to 0, suppose I will do in different way. 2NH3 gas that is going to decompose into N2 gas plus 3H2 gas. Okay, so initially this is like 2 molar is there and this is 0, 0. So if the condition is condition is given, condition is initially N2 gas equal to 3H2 gas. Like initially this is 0, 0 means here this and this are equal, both are 0. So if this initially this is given, this is the conditions, then what is it that component means S minus R. Okay, so S means how many individual components are present, individual species are present. This 1, 2, 3, 3. This R is comes from what is this equilibrium, that is 1. Another is comes from this condition. Condition is initially this exists in equal, so plus, so component is 3 minus 2, that is equal to 1. Okay, but if it says that initially some amount of N2 gas and 3H2 gas is present, means this is present like 0.1 molar and this is present 0.2 molars. Initially it said some amount is present. On that case this condition is not satisfied. Condition is what? N2 gas equal to 3H2 gas. This is not satisfied because initially it says that some amount of this and this present. So this condition is not satisfied. So S equal to S minus R. In that case, see SH3, but this is already present in initially, so that one we are getting 1 plus 1. Here this one will not come, only these conditions come from this equilibrium only. So here C equal to 2. Okay, so this is the conditions. Like if we say that condition, if initial this is this equal to this, then on that case we have to take R each 2, and if not, if initiation present is there, then condition is not satisfied. On that case we will take that is 1, that is, so component is equal to 2. And like if gases are like CO2, O2, N2, this is present, they are chemically not reactive. So if they are not reactive, then no equilibrium states will form. So if no equilibrium state will form, then what? So if he says that if they are not react chemically, then the equilibrium state will not form. If equilibrium state will not form, then this is not present. So if it is not present, and most probably if no reactions, no chemically reactions is not happening, then the condition is not there. Then if condition is not there, then what to say that C equal to S minus R, but no condition is there, then this stands to 0. So C equal to S. If no condition or equilibrium is not present. Okay, and if equilibrium is present, then let's say so if condition is not there, then that how many components is equal to that species. But if equilibrium is present, then components is greater than that species. Components is greater than species. No. So components is less than species, because that species is how many? Yes, species is 3, S is 3, but components is that S minus condition. So S is 3 minus condition is 1, so 2. So species is 3 and condition is 2. So this is if condition is, if no condition or equilibrium is not present, then C equal to S, that component is equal to species. And if that equilibrium condition is present, then what happened, that components is less than species. So components is less than species, or species is greater than components if condition is present. If condition or equilibrium states is present. Okay, and then third terms we will discuss, that is degrees of freedom. Degree of freedom, or this also you can say that variations, that is defined as F. Okay, so this F, although it's not, if I explain also you will not understand it. So when you go through these chapters, you will understand that what do you mean by F. F is mathematically, F is C minus P plus 2, where C is components and P is page, how many pages is there, and F is degree of freedom. So F is generally that how many variables are needed, means how many variations or how many variables are needed to explain a point. That is called degree of freedom. So we will discuss more about it when you go through these chapters. While you are discussing one components, two components, on the time if we say that what is the f means to discuss about one points, how many variations are needed. So that is called f. Okay, so this f it will clear when we proceed the chapters. So today after this, thank you.